Okay, we made it to lecture number 27. That's a lot. Can you hear okay in the back? Acceptable? Louder? Okay. Announcements. Homework number 7 is due on Wednesday. It's in Scheme, and it's pretty long. How many people have started the homework? Okay, good. If you need help, there will be a homework party, 5 p.m. tomorrow in 2050 VLSB. In addition, if you want points back for composition scores on projects 1, 2, and 3, turn those in by a week from today. How's that going? You've realized it's an elaborate ploy to get you to read the comments that we made. There was a time when we made all comments just by writing pencil on printed out versions of the projects, and nobody ever picked them up and read the comments. And that made us very sad. So now there's this. Now we're very happy. There will be a quiz released tomorrow. It will be due Thursday. And as usual, it is open note, open interpreter, but closed classmate, closed internet. Solve the problems yourself, please. And it's about Scheme, just to make sure that you're understanding the fundamentals of the Scheme language to prepare you for Project 4. Project 4 is building a Scheme interpreter in Python. It's ready, but I've just asked a few of the staff members to make sure there aren't any bugs before I release it to you, so I think it will go out tonight. It's big. It is the biggest project ever. So, make sure you start early, and, you know, maybe you could do it in multiple nights instead of just one night. It is released for quite a long time. So it's due Thursday for 23. Today is only the 6th. Are there any questions about that? Well, how can you have questions about a project that isn't even released yet? This entire lecture today is basically just describing to you how to do different parts of your project. Because people don't just build interpreters on their own without some structure. Over the many years that people have been building interpreters, we've realized that some fundamental ideas about how to structure that computation work well, and so I'm going to share some of those with you, and then you can use them as you're building your project. So, interpreting Scheme. This is a structure of a Scheme interpreter. It's also a structure of an interpreter for pretty much any interpreted language that has functions, and that's most of them. So here's the basic structure of the interpreter. We actually saw most of this picture when we built the calculator language last time. There was a function that evaluated expressions, and some of those expressions were primitives, just like the number 2, and some of them were combinations, like when we added 1 and 2 together. And when we added 1 and 2 together, that involved calling a function apply that would apply the addition operation to the arguments 1 and 2. So we see that these two functions, eval and apply, are interconnected, and that whenever eval sees a procedure call, it has to apply that procedure. There are base cases to eval, which is a tree recursive function. When it reaches a primitive value such as a number, then it just returns that value. It does make recursive calls. So, when you have an operator and some operands in an expression, you have to figure out what procedure you're applying and what you're applying it to. And it was the recursive calls to eval on the operands that let us evaluate nested expressions. So if I was adding the result of multiplying something else, I would evaluate that multiplication first and use that number as one of the arguments to addition. So eval is a tree recursive process. The primary reason why we've spent so much time talking about tree recursion in this course. This also calls apply, when it has a procedure and some arguments, and it wants to apply that procedure to those arguments. So when it's time to actually sum up some numbers or multiply together some numbers, that's the job of apply. What about apply? Well, it was all base cases in the calculator language. All it did was apply built-in primitive procedures. We had to write down within the body of calc-apply, here's how you sum, here's how you subtract, here's how you take a product, here's how you divide. But today we're going to add more cases. One case we're going to add in eval is how to look up values bound to symbols. So we'd like to be able to give things names and then refer to those names. And doing that is going to require introducing the idea of an environment. We'd also like a new kind of recursive call that evaluates the sub-expressions of special forms. What's a special form? It's anything that's not a call expression, such as an if, or a cond, or an and, or an or a define. So some of those have sub-expressions that we need to evaluate, which involves more recursive calls to eval. But perhaps the biggest change that we'll make today is that we'll be able to apply procedures that aren't built in. They're ones that we define ourselves. So a user-defined procedure gets created using a lambda expression or a define expression. And when you call a procedure that you defined yourself, all you're doing is evaluating the body of that procedure. So eval says, I found a procedure, please apply that procedure to its arguments. And apply says, okay, the way I'll apply the procedure to its arguments is I'll eval the body of the procedure. So in fact, this is a mutually recursive process where eval calls apply every time it finds a procedure, and apply calls eval every time that procedure was defined by the user using a lambda expression or a define expression. This is the structure of an interpreter. And oh, is it important? Are there any questions? Okay. So we're going to have to add some new things. I showed you the full implementation of the calculator language. If you ever want to look at that on your own time, it's linked here from the top of the course website. But now we're going to need more stuff. We're going to need an environment in which we can look up symbols. We're also going to need to be able to create new environments each time a user-defined procedure is applied. So if you remember back to how Python works, every time you call a function that you defined, you have to introduce a new frame. And that's something that the apply function is going to do. It's going to say, oh, this is a user-defined procedure. I need to construct a new frame. In that frame, I'll bind the formal parameters to the arguments that I'm going to apply this function to. And then I'll evaluate the body of the function. So all that spiel I've been giving you about how functions get applied for the entire course, today's the day when we actually write code to do that. Okay. Before I show you the code, a word about special forms. So in scheme evaluation, the scheme eval function is going to decide what to do with the expression that gets passed in based on what kind of expression it is. So if it's just a symbol, like the symbol plus or the word integer, it's going to look that up in the current environment in order to get whatever value is bound to that. Any self-evaluating expression, such as a number, will evaluate to that number. Anything else has to be a scheme list. Those are called combinations. So things like call expressions and also if expressions are all just represented as scheme lists. So the code that you write in a scheme program is just a list. So here are some example structures. You can say if, and then some predicate expression, some consequent expression, and some alternative expression. or you can say lambda to define a new procedure, or you can say define, which binds some name to the value of some expression. If you don't see one of these special keywords in the language at the very beginning, in the first position of the combination, then it's treated as a call expression. So call expression is the default behavior, where it assumes if it's not an if or a lambda or a define or an and or an or all the other special forms, then it's just a procedure call. And if you got confused between procedure and function, they're the same thing. Just Python calls them functions and Scheme calls them procedures. Okay. So special forms always can be identified by looking at the first element in this list. If it starts with if, it's an if expression. So part of the interpreter's job is to enumerate all of the different special forms and say, here's how you handle the ifs, and here's how you handle the lambdas, and here's how they handle the defines. And once you've done checking all of those, well then the only thing left is that it must be a call expression where you evaluate this operator to get a procedure and apply it to the values of these operands. So any combination that is not a known special form is a call expression. Question? Okay. Here's a question for you. What does that do? This is just supposed to get you familiar again with what's going on in Scheme and what's all these ifs and whatever. So answer yourself two questions. What is demo? And what happens when you call demo on list 1, 2? And then we'll watch the Scheme interpreter do it for us, and we'll find that it was much easier just to ask the Scheme interpreter. But before we do that, talk to the person next to you, try to figure out what demo does and what demo of list 1, 2 will be. Go. Okay, can anyone give me a suggestion for a better name for this procedure than just demo? Put 3 at the end. Yeah, that's pretty good. Okay, so what demo does is it takes in a list, gives you back another list, which has all the elements of the original S and also 3 at the end. So if you pass in an empty list, you'll get just the list containing 3, and otherwise that 3 gets stuck at the end through some manipulation of linked lists in Scheme. Okay, now for the actual demo. First thing I'll show you is here's the Scheme interpreter. This is the project that we're going to distribute to you. It has a function right at the top called Scheme eval, which takes in an expression and evaluates it. What do I mean by that? Well, an expression would be something like +2, 2 in Scheme, which is represented in Python as a linked list where we use the pair class I told you about last time to link together a bunch of elements. So it's plus as the first element, and then 2, and then 2. And when I call Scheme eval on that expression, I get 4. Now it doesn't just take an expression, it takes an environment in which that expression is evaluated. And here in this example, we just created the global frame for our environment, but in general, the environment holds all the bindings between symbols and their values that we're going to use in the process of evaluating this expression. Okay, now it turns out that as part of the project, I just give you all the code for scheme eval. So let's walk through it together, see if you have any questions. It's either the case that the expression that comes in is an atom, meaning some primitive expression, at which point, if it's a symbol, we look it up in the environment, or if it's self-evaluating, then we just return the expression itself. Self-evaluating is things like numbers, true, false, and in fact, in this version of Scheme, there are even things like strings supported. So here, if you want to see the whole list, there it is. And OK is a representation of some undefined value, kind of like none in Python. Okay. So these are all base cases. What's the non-base case? Well, that's if the expression is a list. Now, it has to be a well-formed list, meaning the first element is anything, and the second element is a list or nil. So we check for that. We get the first element, and the rest of the list, we check and see if first is in a dictionary of special forms. If it's a special form, then we get a function that handles that special form. So let me show you all the special forms in the whole language. There's and, begin, can't, define, if, lambda, let, or, and quote. Eventually, you should know what all those mean. I understand if you haven't figured it all out yet, that's totally fine. But this is the subset of the Scheme language that you're supposed to learn in this course. Okay, so if it's a special form, then we have to look up some function that handles the special form. Every single one of them is different, and most of the project is in implementing each one of those. So how do you handle a lambda expression, or how do you handle define form, or whatever? If it's not a special form, one of the keywords that we know about, then I recursively call scheme eval on the operator expression in order to get a procedure. I recursively call scheme eval on each element of the rest, meaning all of the operand expressions, in order to get the arguments, and then I apply the procedure to those arguments in the current environment. What's scheme apply? Well, scheme apply takes a procedure and some arguments and an environment. If it's the case that the procedure is primitive, meaning it's built in, like plus or times, then I just apply that primitive procedure. And what's going to happen in apply primitive is we'll ask Python to do the work. So every programming language gets implemented in terms of some other programming language if you're building an interpreter. And here's where we'll go find a Python function that actually does the summing, and we'll sum in Scheme by summing in Python. You have to fill that in. And what if it's not a primitive procedure? If it's a user-defined procedure, that means it was created by a define expression where you said what the body is that gets evaluated. So we make a new frame where we bind the formal parameters of the procedure to the values of the arguments, and then we evaluate all of the procedure's body in this new environment. And what is eval all? Well, that just takes a bunch of expressions and calls scheme eval on each one. Now, right now, it just calls scheme eval on the first one. You have to implement the rest. Okay, so is it the case that scheme eval calls apply? Well, sure, right there. And does apply call eval? Well, it calls eval all, which calls scheme eval. So these are mutually recursive functions. Question? Correct. So primitive procedure is built for you. It's in a file called scheme primitives. There it is. A primitive procedure is really just a Python function that does all the work. And what about a user-defined procedure? Well, the only one we'll talk about today is a lambda procedure. And the lambda procedure takes some formal parameters, a body, and a parent environment. And that's all you need to apply a procedure. This is in scheme.py, which is the main file. Okay. So what I'm going to do is I'm going to trace scheme eval, but I'm going to run a version where the answers are already filled in, and we can watch what it does. Scheme.py. If I evaluate the number 2, then it's going to call scheme eval on the number 2 in the global frame, and 2 evaluates to 2, and so we see 2. Well, that was the most boring example ever. Okay, what if we add 1 and 2 together? Now it's getting interesting. Here's what you do. You evaluate the list plus 1, 2, which is a combination where you have to evaluate the first element, the operator, which gives you the procedure that adds. We evaluate the 1 to get 1, we evaluate the 2 to get 2. Adding 1 and 2 together gets you 3, and you're done. What if you want to add 1 to the product of 2 and 3? Okay, so that means you have to evaluate this whole thing, which means adding together 1 and the result of multiplying together 2 and 3. By the way, that's 6, and adding 1 and 6 together gives you 7. These are all just recursive calls to scheme eval. Scheme eval does all the work. That's how interpreters work. Question? Oh, so what's going on in this trace? The way a trace works is every time a function gets called, you see what's being called on what arguments followed by a colon. Every time it returns, you see the same thing but with this arrow. Now sometimes when there's a lot of work to do, there's stuff in between. So here's the original call to scheme eval, and it didn't return until way down here. It returned way down here because it had to do all of this intermediate work to figure out that the value of this was 7. But when it's just a base case, then the thing returns right away. So that's how the trace functions. Okay, so now we know what work happens when we evaluate a nested expression. What about when we evaluate demo? Okay, so demo took in some list S, asked whether it was the case that S was empty. If S was empty, it returns a list containing 3. Otherwise, what it returns is the result of consing the car of S, meaning the first element of S, onto the result of recursively calling demo on the cdr or rest of S. Close the cdr, close the demo, close the cons, close the if, close the define. What happens when I hit return? Actually, not much. Okay. Sorry, it's too long. But what happened is I evaluated this define form, and what happens when you define a procedure? Well, nothing. That procedure's name gets bound to a new procedure in the current environment, and what define does is it actually returns the name. So the return value is demo. At the same time, we've altered the environment, so the demo procedure now exists. We haven't called it yet, so we haven't evaluated its body. The way we call it is we write a call expression that starts with demo and also gives it an argument, the result of calling list on 1 and 2. Now maybe we'll see something exciting. Oh yes, we did. All right, what happened? Well, a lot of computation is required in order to evaluate this expression. Is this big enough, by the way? Bigger? No votes for bigger. Okay. 1 vote for bigger. Ah, too big. Okay. Let's see if we can figure out what's going on. So we're evaluating demo list 1, 2, which means I have to figure out what demo is. What's demo? Oh, it's a procedure that has this body. Okay, what's list 1, 2? Well, I have to figure out what list is. It's the built-in list, which takes 1 and 2 and gives me back a list with 1 and 2 in it. So list is a really simple thing. Okay, now what happens? After I figure out what I'm applying, which is this procedure, and what I'm applying it to, this list, I then have to evaluate the body of the procedure I'm calling in a new environment where the formal parameter is bound to the argument value. That's what this next line says. Over here, this is the environment. Sorry, it's kind of cut off. So let's shrink it a little bit. So this environment says S, the formal parameter of the demo procedure, is bound to 1, 2. And then there's the global frame, which has all kinds of stuff in it. We don't write it out. But this is a new environment than what we were in before. Before, we were just in the global frame. In this new environment, we're going to try to figure out what if null, then 3, otherwise cons car, demo could, or whatever does. Which means we just start applying our procedures. So we call do if form, and the if form is evaluated by first evaluating null of S, where null is a procedure that asks whether something's null. Is 1, 2 null? No, it's not. And so I then evaluate the alternative expression here, and you can see that appear right here. Here's the alternative expression. Question so far? Yeah. That's right. Lambda is just how we draw a procedure that a user defines. Okay? So we only got like a little bit down. So what happens next? Okay, question. Yeah, so a lot of the project is saying, here's how you evaluate an if. You look at the predicate, you evaluate it. So that means call scheme eval on the predicate. If you get a true value back, then call scheme eval on the consequent. Otherwise, call scheme eval on the alternative. So it feels basically like you're translating the scheme evaluation procedure into Python. That's exactly what you're doing when you write an interpreter. Question in the back. Yeah, so every scheme value is represented as a Python value. Numbers in scheme represented as Python numbers. Boolean values represented as Python Boolean values. Scheme lists are represented as instances of the pair class. And the pair class is like the linked list class. Okay. But, I mean, if it's bizarre that we have, like, multiple programming languages all going on at the same time, that's because it is bizarre. We're interpreting one programming language with another one. Okay. So I wanted to show you this cool moment where we try to figure out what cons car demo cooter is, which means figuring out what demo cooter is, which means figuring out what the cooter of S is, which is the list 2. And then we have to call demo recursively with the argument, which is the list 2. And so then we see for a second time a change of environment. So we used to be in an environment where S was bound to 1, 2. Now we're in an environment where S is just bound to 2. And if you keep going down farther, we'll eventually end up in an environment where S is bound to null. Okay, it's a little bit hard to see, but such an environment is right here. Now what happened to those other environments? Well, those other frames are still around because we have to go back and evaluate what it means to cons on the car of S to the result of calling demo on the cooter of S. And that might require the environment. So you see, like, way later on in the computation, we go back from having S bound to null to a different frame in which S is bound to 2. And there's still the frame where S is bound to 1, 2, and eventually we get the result, 1, 2, 3. Question? this display says global frame always is that it's showing you the whole environment, which is a sequence of frames. So it shows you the first frame in which S is bound to 1, 2, and then there's a little arrow saying the parent of that frame is, and the parent of the local frame in this case is always the global frame. So that's why it shows up everywhere. So that means any of these expressions that references something in the global frame, we'll find it. So I think when recursion happens, nothing goes away. You still have different frames remembering different values for S. And what we're seeing here is that just different expressions get evaluated in different frames. Kind of like what you'd see in an environment diagram. This is a little bit harder to read than an environment diagram, but it's actually the same mechanics going on. This magic true, just forget about that. I agree it's there. It's for the extra credit problem in the project, which I'll talk about on Wednesday. Okay. Were there other questions? Let's move on. Okay, so we saw the demo. Now we're going to talk about some of the parts that you built. So you implement how to handle every special form. So the logical forms are special forms where not every sub-expression gets evaluated. So for instance, the whole point of if is that you only evaluate one of the consequent or the alternative, not both. And so you have to write Python code that makes sure you only evaluate one and not the other. And or are special forms because they may only evaluate a subset of their sub-expressions. So the way and works is it goes from left to right until it finds something false, and then it returns false. If none of them are false, then it returns the value of the last sub-expression. Now what about or? Or goes through evaluating each sub-expression in order until it finds a true value, and that's the value of the or expression. So we call and or short-circuiting because they don't always go through all their sub-expressions. And this is true in Python as well. If you and a bunch of stuff together, you may only get some of it evaluated. Have we talked about cond? It's in your homework, right? Okay, so if you've done your homework, you know about cond. If you haven't, too bad. But the point is, a cond expression will only evaluate one of the sub-expressions marked with an E here, like E1 or En or E, corresponding to the first predicate that defines true. It's like a big if, elif, 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 else. Okay, we're just going to focus on if for a little bit. The value of an if expression is the value of one of its sub-expressions. And so here's how you evaluate it. You evaluate the predicate, then you choose one of the sub-expressions based on whether the predicate is true or false, and then you evaluate the sub-expression to get the value of the whole expression. And all this happens in do-if form, which is a function somewhere in your project, do-if form, that you have to evaluate. So you have to figure out what to do with the three expressions that come in. And big hint, it involves a lot of recursive calls to scheme eval. Okay, so what happens if you write such a thing? Here's the kind of output that you'll see. If I write if true, then 3, else 4, it will evaluate if true 3, 4 by first evaluating true, then evaluating 3. What happened to 4? Well, 4 was the alternative that was never chosen. So even if I put something that had an error in it, like dividing 1 by 0, it wouldn't matter because the alternative never gets chosen. Now if we did choose the alternative by putting false here, then I would get an error division by 0. And I would never evaluate 3. Okay, so what is this huge mess on the screen? Well, this just says in order to evaluate the whole thing, I have to figure out what false is, it's false, and then I have to divide by 1 by 0, which means dividing 1 by 0, Oh, that's bad. Scheme eval exited via an exception, and the exception happened right there, which was part of this. Talk to me, people. Questions? Okay. What about quotation? That's something we talked about. The quote special form evaluates to the quoted expression. The quoted expression is not evaluated. So if I quote an expression, such as quote plus 1, 2, it will evaluate to the list, which has 3 elements, plus 1 and 2. Plus is a symbol, 1 is a number, 2 is a number. The expression itself is the value of the whole quote expression. So the value of quote plus 1, 2 is plus 1, 2. By the way, putting a single quote in front of an expression is just shorthand for the special form, which starts with the keyword quote, followed by some expression. So quote 1, 2 is equivalent to putting a little quote there, and then 1, 2. Why do we have these two different things? Well, this one saves some parentheses. By the way, if you want to see this happen, and you will implement how to handle quotation, where it gets handled, where this conversion happens between an apostrophe and the quote special form, is actually when the expression gets read in the first place. So remember the two parts of the interpreter. First, you have to parse the code. Then you interpret the expression tree. And when we're parsing the string representation, we expand this quotation mark into the actual combination that starts with the word quote. So I'm going to quit out of Scheme, and instead I'm going to open up the Scheme Reader, which we saw in the calculator example. Scheme Reader doesn't do any evaluation. All it does is show you what you typed in. But it gets rid of spaces and lets you go on to new lines and stuff like that. Now, what happens when I quote hello? I get quote hello, which is the same thing as if I put an apostrophe before the word hello. So it's, by the time your quote hello reaches the interpreter, it looks like this. It looks like a list where the first element is the word quote. So that makes everything really look like a bunch of combinations, which makes life so much easier. Then, okay, any questions about that? If I quote 1, 2, I get quote 1, 2. If I quote, 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 quote 3, I get quote, quote. Question? That's right. No, all this is doing is reading in the expression and showing you that expression again with this tiny little transformation that quotation marks get changed. Yeah, so I'm not even really using the interpreter. Okay. So back to Scheme, what happens if I evaluate quote 1, 2? You can see what I'm evaluating is quote 1, 2, and that evaluates to the list 1, 2. So quotation evaluation is just one step because you don't really figure out what the thing is that you're quoting. All right, let's talk about lambda expressions. A lambda expression evaluates to a user-defined procedure. It looks like this, lambda, and then some formal parameters in the body. Here's a lambda procedure for squaring something. The implementation in Python of how we represent lambda procedures is that they have a scheme list of symbols. In this case, it would just be this list containing x. A scheme list of expressions. In this case, it would be the list containing one expression times xx. but you could have more expressions in the body if you want. And finally, a frame instance that tells you the parent of the procedure. So just like in an environment diagram, every function had as its parent the current frame in which that function was defined. Here, every procedure represents its parent as an attribute n, which is just the environment in which it was defined. So how do we represent frames and environments? So an environment is a sequence of frames. We represent that by saying a frame has some bindings and a parent. So a frame is a Python instance of this frame class. It has methods lookup and define. Let's take a quick look at those. Class frame is here. You can look stuff up, and you can define stuff. To define is built for you. You have some bindings between symbols and values, and you just set the binding of this symbol to a value. So really, a frame is just a dictionary of bindings. Now, what about looking stuff up? Well, you have to write that down. One word of caution. In our environment diagrams, we put return values in the frames. We don't do that in the project. They only keep track of the bindings between names and values, but not the return value. So, let's say I want to bind y and z to 3 and 5, and then I want to introduce a new frame that's a local frame with the parent as the global frame, where x is bound to 2 and z is bound to 4. I can do that now in code. What do I mean by in code? Well, here's what I'm going to do. I'm going to start up Scheme interactively in Python, then I'll quit out of Scheme. So now I'm back in a Python environment where I have access to the frame class. In this frame class, I'll create a global frame. And I'll also create a local frame whose parent is the global frame. Now I said I was going to bind y to 3 and z to 5, and then x to 2 and z to 4. So that means saying define y is 3 and z is 5. And in the local frame, I'll define x as 2 and z as 4. Now what have I done? Well, I have a global frame. It has many bindings. Why does it have... Okay, it doesn't have many bindings. It has bindings which are just y and z. I haven't added in all the plus and times and stuff like that yet. And then I have a local frame, f1. And the local frame has x bound to 2 and z bound to 4. And its parent is the global frame. Okay, so G looks like that. Oh, sorry. G looks like that. F1 looks like that. F1's parent is the global frame. What happens if I look up z in the global frame? I'll get 5, because that's the bindings in the global frame. What happens if I look up z in the local frame, F1? I'll get 4, because z is bound to 4. And if I look up x, I'll get 2. And if I look up y, well, y isn't in the local frame, but it is in its parent, the global frame, so I should get 3. That's the behavior you'll have to implement in order to represent frames in your scheme interpreter. Question? F1.bindings looks like that. It's the same as that, except in a different order. Order doesn't matter in dictionary. There was a question. Now it's hiding. Okay. So now you know what a frame is. What happens when you define a symbol to be some value? Well, define just binds a symbol to the value in the first frame of the current environment. So if you have define and then a name and then an expression, you evaluate the expression, you find the name to its value in the current frame. And so if I define x to be plus 1, 2, I have to scheme eval plus 1, 2 to get 3, and that binds x to 3. And what about the other form of define, the one that looks like this, define demo s as blah, 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 blah? Well, that's really just shorthand for define with a lambda expression, where you define the name to be lambda formal parameters body. So we don't implement that separately, we just transform the syntax a little bit. So this thing is the same as that. Identical behavior, so you might as well handle it in identical ways in your project. Okay, so once you have lambda expressions and defines, then you're in a position to actually execute the demo that I showed you at the very beginning. So let's look through that process one more time. To apply a user-defined procedure, we create a new frame in which formal parameters are bound to argument values, and the parent of that frame is the env attribute of the procedure that was being applied. So this is all the logic that has to happen in scheme apply. Then we evaluate the body of the procedure in the environment that starts with this new frame. So every time scheme apply gets called with a user-defined procedure, you create a new frame and evaluate the body in that frame. So back to the original example that I showed you that puts 3 at the end of a list. We are going to have a global frame, and the name demo will be bound to a lambda procedure in that global frame. Then when we call demo on list of 1, 2, we're going to create a list containing 1 and 2, which, by the way, is represented as a pair with 1 as the first element, and the list containing 2 as the second element. We're going to create a new frame whose parent is G, with the formal parameter S, right here, bound to this list 1, 2, and that's the first call to demo. And then we have a second call to demo, which is just the list containing 2. And then there's a base case call to demo, which just takes a nil and returns the list containing 3. So what I've drawn here is a sketch of what the environment diagram would look like in scheme. We don't keep track of return values in the frames. We don't keep track of the names of what function was being called. But we do have to keep track of the most essential part, which is what are the formal parameters and what are the values that they're bound to. Oh, interesting. So every time I've ever taught this class, someone has asked the question, do I have to draw a scheme environment diagram on an exam? Well, it turns out you don't, but you should learn to do it anyway, because I will ask you, what does this scheme procedure do? And the best way to figure that out is by drawing some sort of environment diagram. Cool. So, history lesson. I did not come up with the structure of this interpreter. It dates back to when well before I was born. And what I'm going to show you is the original definition of eval and apply in the Lisp 1.5. My goodness, it's beautiful. So here, we see the exact same structure that we have today. I mean, of course the syntax is different, but you can see many pieces reminiscent of what we're building today. You check and see if something's an atom, or if it's a lambda, and here we're looking at car and coulter and cons and atom and equal as the built-in procedures. If it's none of those, then we just apply the evaluation here. If it's a lambda procedure, then we recursively call eval. So apply calls eval whenever we have a user-defined procedure. And what does eval do? Well, eval checks to see if it's quote or con, the special forms. Otherwise, it just calls apply of the procedure. Anyway, what I told you was a good idea back then. It's a good idea today. I'm glad we could share this moment of just looking at beautiful code from long, long ago. And now you can go write your own beautiful code in Project 4. See you on Wednesday.